So today I will be showing you how to write and balance a combustion reaction. A combustion reaction is special in that unlike single replacement or like synthesis or double replacement, the combustion reactions generally follow the same pattern. So right now we're being told that this chemical right here, C5H9O, is combusted. Basically what it means to be combusted is we're going to take that thing and we're going to burn it. We're basically going to combust it, explode it, burn it. So to burn something, you're going to need oxygen, right? Oxygen needs stuff to burn. Or something that's burning needs oxygen. You should know this. If you ever, I don't know, worked with campfires or anything. Now, when you burn something, it should release carbon dioxide. And it also releases water as steam, as water vapor. So this is a combustion reaction. Whenever you have something that's combusted, it needs oxygen to burn, and it's going to produce carbon dioxide and water. For now, it's unlikely that you'll see anything that breaks this pattern, but generally this is how this is written. A combustion reaction will always have, for the most part, carbon dioxide and water on the right side, unless there is something else attached to here that would become released. Like, for instance, if we had some fluorine in there, we might actually produce some fluorine gas over here, but that's, you don't need to worry about that for now. This is just the basic combustion reaction you're likely to see numerous amounts of times. So right now, I've just written out what the chemicals are supposed to be. I haven't balanced it yet. For now, we will be doing the balancing. First, we'll start with our carbon. Looks like over here we have a total of 5 carbons, but only 1 over here. So I'm going to go ahead and we'll put the 5 down here because I suspect that I'm likely going to have to change it in the future. So that gives us 5 carbons. Next, we'll try our hydrogens. So we have 4 over here. So I'm going to put a 2 down here and see what that gives us. So right now our carbons and hydrogens are balanced. We'll have to look at our oxygens next, because that seems like that's the last thing available. Looks like on the right side, we have 3 oxygens. And on the right side we have basically 2 oxygens from here and 10 oxygens from here, because we have 2 and 2 oxygens in each compound, and we have 5 of them. So this means we have a total of 12 oxygens on this side. Now, unfortunately, something specific is happening here. If we look over here, we have a single oxygen, and that's bad, because basically our oxygens on the right side is even. We have 12 of them. To get our oxygens on the left side to be even, we need to make sure we get rid of any odds, because any odds will just add up to make another odd. So looks like we have 1 oxygen here. We're effectively going to have to double everything, and I suspect that will be our final thing here as well. But if we take a look over here, now we have 10 carbons. So we're going to have to come back in, put a 10. This is the new value. I like doing this because when you're balancing reactions that get a little bit involved, you might have to change the numbers you initially put. Whoops, let me get rid of these circles. So we have 2 over here, and I'm putting this 2 so I can double this oxygen. So we're going to put the 10 for carbon. Next we have 8 hydrogens over here, so looks like our new number is going to be 4. Now 4 times this 2, going to give us that 8. Now we're going to look at our oxygens. Looks like on this side we have 2 oxygens, and on this side we have 2 oxygens as well. So a total of 4 oxygens on this left side. Over here we have 20 oxygens on this one, and 4 oxygens over here. So on the right side, we're going to have 24 oxygens. Now, there's a simple way to combat this. Basically, we don't want to be changing this value. We don't want to change the stoichiometric coefficient for this compound, because as you saw before, if we change this value, we're going to have to change our carbons and we're going to have to change our hydrogens. But we do have a floating oxygen over here that we can freely manipulate. If we need a total of 24, right now we have 4, we can say that these 2 oxygens that come from here are fixed. We probably don't want to be changing those, because again, we'd have to change all our carbons and all our hydrogens. So in essence, we've got to work with these 2 oxygens over here. And because we're reserving these 2 oxygens as used up, we can say that we need to make up what's left. We need to make up the rest of the 22 oxygens. Now, this one's a pretty intuitive process, but we'll have 11 for our stoichiometric coefficient. I'll put it up here. Because if we have 11 of these, each of those has 2, we make up the 22. So now we have 22 in there, plus this 2. That's going to be the 24 oxygens that we need on both sides. Okay, now I'm just going to go ahead and rewrite this reaction, make it a little bit neater. So we're going to have 2 of this compound. It probably has a name, but for now, you could also use your covalent naming conventions and call this your pentacarbon tetrahydrogen monoxide. Let's see. Okay. So we have 10 carbon dioxides plus 4 waters. Now, there's something unique about this reaction in specific. Usually any combination, combustion reaction, they have a certain quirk, and that is usually you can't have fractional coefficients, meaning this can't be like 3/2 or anything. But whenever you have diatomics, meaning these, oxygen, and just to give you a quick refresher, diatomics are going to be these elements over here. Honkobriff. It's a quick mnemonic. But basically, what this means is that if you ever find these elements as a gas, they're going to be diatomic, which means they're going to have 2 atoms for each molecule. So hydrogen gas is going to be H2. It's just going to be a bunch of H2 floating around. Same thing for O2, N2, Cl2, Br2, iodide 2, and F2. So these are going to be your diatomic gases. Important. So the quirk about these diatomic gases is that since effectively they're doubled, what we can do is we can actually put a fractional coefficient for a diatomic. So what you could do, and this is correct, this is the solution, one of the solutions to the balanced combustion reaction. However, another one is going to be this. Whoops, that's a H40 plus 11 over 2, 5 carbon dioxides plus 2 hydrogen monoxide water. Okay, so you might notice that what we did was we just simply halved each coefficient. You can think of it like we divided everything by 2. So this 2 divided by 2 became this 1, 11 over 2, 10 divided by 2, and 4 divided by 2. Now, the reason you might want to do this, simply besides that you can, these are both valid answers. Whoops. Both of these are valid answers to the combustion reaction that are balanced